Welcome back, my dear fellow physicist. Today we will be starting our second lesson in simple harmonic motion, the idea of waves and wave behavior. Now, when modeling simple harmonic motion, as you might have noticed from the graph, it's most easily modeled in the form of a wave because the graph is sinusoidal, which is like little waves, right? Like little waves. And so we model these simple harmonic motions in the form of waves, which waves, in this case, have several properties. These properties are, the first of which being reflection. If you think about it, when a wave hits a wall, it reflects. It just goes up to that wall there, and then it reflects in the opposite direction. Pretty straightforward. Refraction, which is a bit more complicated. It's when the wave enters a different medium it bends. Now, what does this mean? Well, most obviously, it means it changes direction. If you're looking at the wave from above and it's moving like this, once it enters that different medium, it might start moving like that. But it also may change speed or wavelength. Values which are reflected by v or lambda, which we'll explore more once we get to water waves and light waves. Third property is interference, which simply means when you have two waves and they combine, right, they make one big wave. That's sort of the idea of interference. And diffraction, which is the idea that when the waves go through a small opening, they spread out from that opening, as if it's a new source of waves. And that's the idea behind diffraction. So those are our basic properties of waves. So what is a wave? Well, a wave is simply a transfer of energy from one place to another. Think about if you dropped a pebble in a lake. Once that pebble is dropped in the lake, the kinetic energy of that pebble turns into waves in the lake, which spread out, transferring that kinetic energy throughout the lake. That's all a wave is. It is kinetic energy. So to start off with our analysis of waves, let's start off with the simplest idea of a wave pulse. Now imagine you have a string in your claw-like hand here, and you shake it once, creating a little bump that travels along the string. That right there is a wave pulse. A wave pulse is just a single transfer of energy. Now there are several properties of a wave pulse that we can discover. The first of which is the reflection property, which is if the wave pulse hits a wall that is fixed wall, it's fixed to that wall, and when it reflects, it will reflect opposite. It'll be upside down now. That's what happens after it reflects. However, if the wave instead encounters a moving point, let's say that your wave is connected by a ring to a pole, well, that's going to be slightly different. It will reflect identically. This one's up, this one's also up. So that's the properties of reflection from rings and from wave pulses. And another thing is the interference property. We don't really talk about refraction and diffraction yet because those are more continuous wave properties. For this, we talk about superposition, interference, and that is when you have two waves that are identical in phase and they collide, they create a big wave. That's called constructive interference because it constructs a larger wave. However, if they're out of phase, if they're opposite waves and they collide, they will simply cancel each other out, creating a straight line, which is called destructive interference because it destroys the wave and creates just a straight line. And that is the whole idea behind the wave pulse there. Now, what happens when we have multiple wave pulses? Wave pulses all together. That is called a continuous wave or a transverse wave. So if you instead grab the string, you just kept shaking it. You just kept shaking it and kept shaking it, you would get something like that, which is a continuous or transverse wave. That's the idea of a continuous or transverse wave. Now, there are several ideas behind this wave, the first of which being wavelength. A wavelength is simply the length between one point in the wave to the next identical point on the wave, which would be from this screen. In this example, one crest to another crest, or maybe it's one trough to another trough, or one midpoint to another midpoint. That is a wavelength. All these distances are going to be the same. Wavelength is measured in meters and represented by the symbol lambda. It's a little Greek version of L. Another property of a wave is the frequency, which, as we discussed earlier in our first simple harmonic motion lesson, is simply how many oscillations happen in 1 second. And so that would be how many wavelengths actually pass by in 1 second. Frequency is measured in hertz, which is 1 over a second, and the symbol is the cursive F. And the final idea that we will be looking at here is the speed of a wave. How do you calculate the speed of a wave? Well, for transverse waves, the formula for its speed is the speed, or V, equals your frequency multiplied by your wavelength. Simple as that. Because if you think about it, speed is meters per second. This is 1 over a second. This is meters. Multiply, you get meters per second. You can often use units to find your formulas. Now, a final concept we'll talk about when talking about continuous transverse waves is polarization. And polarization is the idea of a wave that travels only in one dimension. If a wave travels only in one dimension, it is said to be polarized. So, for instance, this wave you created with a string, if you were to put it through 2 panes here with a vertical hole, right, it would pass straight through. But if you were to create another 2 planes, which had a horizontal hole in them, it wouldn't. It would stop. It would cease to be. Because the wave doesn't travel horizontally. These walls would cancel out the wave. And that is a polarized wave. This idea is explored more in depth when we get to light waves. But that's going to be a few videos from now, so don't worry about it too much for now. Now, we can graphically represent these wondrous waves, these wondrous transverse waves, and we can represent them in 2 key ways, the first of which being displacement time graphs. And that's simply going to be your classic displacement over time graph. And it's going to look it'll look something, you know. You're going to have, it's going to be cosinusoidal or sinusoidal or some form of the curvy curve graph, and you can basically tell the displacement from any given place. This is going to be the equilibrium position. This is going to be the maximum amplitude away from the equilibrium position. It's just simple harmonic motion. However, there's another unique way that we can graph this, and that is displacement position graph. Now, what's the difference, you ask? If you remember from our very first videos, displacement is a vector, while position is a scalar. So when you graph your displacement versus your position, you are actually going to get a snapshot of what your wave looks like in that particular instance. Because while on the displacement scale, from equilibrium, you may have moved in a certain area and then you move back to equilibrium. When you're moving position, well, even if you're just oscillating back and forth, you're still covering more position because position is not a scalar. And therefore, you get a snapshot of your wave. It's very useful for having a snapshot of what your wave might look like in that instance. Now to discuss standing waves. Standing waves are a bit different from continuous waves because they occur when you have 2 continuous waves in a closed-in space that superimpose on one another. Waves that are coming at each other from different directions and collide and end up forming a superimposed structure that looks a bit like that. Now, what is the whole idea behind standing waves? Why do we care? Well, the reason we care is because a standing wave has several marked differences from the transverse or progressive wave that we've been discussing earlier. Now, the first of which is going to be progressive waves move. They move through medium, they keep on traveling. However, standing waves do not. Standing waves are trapped between two ends. They're constantly superimposing on themselves. That's why you get that shape, that kind of like a bunch of balls in a row sort of shape. The second marked difference is that in a progressive wave, all locations are out of phase. If you remember phase from our first video, what this means is that if you take a snapshot of a progressive wave, in one instance it might look like that, in the next instance it looks like that for the same area. So these areas now, they're out of phase. They're out of phase. However, in a standing wave, all locations are in phase. Which makes sense. If you look at this image here, you'll see that every single location is in phase with the next. It's always like this. It creates a perfect little circle area. They're all in phase. They're never out of phase. One location will always be like this. It doesn't change into something else like the progressive. And the third marked difference, and arguably the most important, is that in the progressive wave, because all locations are out of phase, every point achieves amplitude, or maximum distance away from the equilibrium point. Every point of a progressive wave, eventually, they're all at the equilibrium point, then the wave passes through, and all those points there will eventually get to the amplitude as the wave passes through, right? However, in a standing wave, there are certain points which never leave equilibrium. And if you look at our standing wave, it's easy to see why. All these points here are stuck at equilibrium as it rotates. These are called nodes. Nodes are the points that never leave equilibrium. However, these points up here will never reach equilibrium, will they? And we call those antinodes. And those are the key features that are coupled with standing waves there. Now, the idea of the standing wave, is the whole idea behind stringed instruments. Stringed instruments create standing waves. That's what they do. And these standing waves end up creating higher harmonics. And what is a harmonic? Well, if you think of a standing wave on an instrument, it's got an end. These ends have to be notes. You can't have the end rotating up and down. They're stuck. Now, different waves can be formed. You can form a standing wave that looks like this, right? Or you can form a standing wave that looks like this. Those are different harmonics. They'll create a different frequency of sound. Now, in a guitar string, the idea with the harmonics is that you're going to get the first harmonic, which is considered this one. It's the simplest thing you can have on a string when you have standing waves on a string. Is harmonic first is going to be the speed over twice the length. Well, now why is this? Well, if you look to find the frequency, speed over wavelength. Well, what's the wavelength of this? Well, if you pretend that this is a full wave, it would continue on over here, and that would be one wavelength. What's that? That's twice whatever the length was. So that's how you get the first harmonic. The second harmonic, because that is a full wavelength there, harmonic 2, right here, is just going to end up being V over L, which means that every harmonic increases its frequency by a factor of 2, creating standard notes that we get on our scale, C, D, E, those sort of things. They increase by a factor of 2 the frequency and create higher notes. That's the whole idea behind music in general. And that is quite a beautiful thing, I think. Now, the thing about guitars, though, and strings especially, is that they'll vibrate with all sorts of frequencies, but only those frequencies that have nodes at either end of the guitar string will resonate and form the note that you want to hear. So let's say if you had a frequency that looked like that. Well, those aren't notes. So that frequency doesn't form. Only this one forms, the circular one. And so that's the note that is heard. Now, how does a guitar work? Well, some of the notes have more mass per unit length or density in them. And that means that the wave will travel slower because waves travel slower through more dense mediums, which creates lower notes. That's how you get a scale of notes in your guitar. Now, to play higher notes, you can shorten the string by pressing down at a spot. Let's say you have a string here and you press down there. Well, now you've created just a new end and you've created a new note. So you can create a shorter wave, which will have a higher frequency and therefore a higher note. Or if you let go really quick, you can make that the middle note and create a higher harmonic. And that's how guitars work. And that really is a good example for just explaining how standing waves work in general, with the frequencies equaling higher sound. Because, speed is always the same. Now, however, there's one last wave that we must discuss before this video is over. And that is kind of a new type of wave. We've been discussing transverse waves. Waves that go like this, sort of wavy in a string or something. However, there is a new type of wave in town, and that is the longitudinal wave. Why do we care? Well, because longitudinal waves are like sound waves. But because sound waves are a bit too advanced for now, I'm going to cover the example as in a slinky spring. Remember those old slinky springs, right? Now imagine you just push a slinky spring and create a wave pulse in it, which you can do. It would look something like this. You have these compressed spots, or spots of compression, and these kind of stretched out spots, which are called spots of rarefaction. And that's a wave. That's simple harmonic motion right there. And in the same way that transverse waves reflect off walls, so do longitudinal waves. In fact, the entire purpose of this example is to show that longitudinal waves are in essence just like transverse waves. You can make the same graphs of displacement versus time, or displacement versus position. They're going to look about the same. It'll appear to be a transverse waves on a graph, but it's a longitudinal wave. And that's to show that we can study sound in the same way that we can study all our other waves, but that is for a different video. That is all I have to say about waves. Join us next time where we'll talk about waves in 2 dimensions, more specifically, water.